Suppose you want to know the average height of every adult in your city. Measuring all of them is impossible, so you measure a sample, let's say 1,000 people, and calculate their average instead. But the problem is that this average depends on which people happen to land in your sample group. A different 1,000 people would have given a different average. On its own, the sample mean says nothing about that uncertainty, so it looks more exact than it really is. So, a confidence interval is a range of values that is likely to contain the true population mean. Instead of a single figure, it gives you a band that the true value probably falls within. So instead of saying the average height is 175 centimeters, with the help of a confidence interval, you can say the average height is between 173 centimeters and 177 centimeters with 95% confidence. But what does 95% confidence actually mean? You will most often see 95% confidence intervals, and this is where almost everyone gets confused. It is tempting to say there is a 95% chance the true average lies inside this particular interval. That interpretation is actually wrong. The true average is a fixed number. Once the data is collected, it either falls inside your interval or it does not. There is no probability left to assign. The correct interpretation is like this. If you repeated your study many times, each time collecting a fresh sample and building a new interval, about 95% of those intervals would contain the true value. And I know this is a little confusing. Confidence intervals belong to frequentist statistics, a school of thought that says probability can only be defined for things that are genuinely random. But the true population mean is not random. It is a fixed number that already exists even though you do not know it. So, how do you calculate confidence intervals? For a confidence interval around an average, the formula is as follows. The interval equals the sample mean plus or minus z times the sample standard deviation divided by the square root of n. Let me explain each part. The sample mean, written as x bar, is the point estimate. Sigma is the standard deviation of the data. If you wonder how to calculate the standard deviation for your sample, you can watch the video highlighted in the corner. N is the sample size, and Z is a critical value that sets the confidence level. The result has the form estimate plus or minus the margin of error. Here's the height example worked through. Suppose you measure 1,000 adults and get a sample mean of 171 centimeters, and the standard deviation is 16 centimeters. For a 95% interval, Z equals 1.96. So here's the confidence interval, 171 plus or minus 1. This gives a range from 170 centimeters to 172 centimeters. So, what changes the width of your confidence interval range? 3 things determine how wide the interval turns out. First, the confidence level. A higher confidence level requires a larger z. Being more certain, say 99% instead of 95%, widens the interval. This is the cost of being more certain. That is why most work sticks with 95%, which is already more than reliable enough for most purposes. Second, variability in the data. The more spread out your sample is, the wider the interval, because a noisier sample tells you less about the true mean. Third, sample size. A larger sample narrows the interval. Since n sits under the square root in the formula, more data shrinks the standard error and sharpens the estimate. So, if you want a tighter confidence interval, you can collect more data. Of course, that usually comes with additional cost and time, so there's always a trade-off. And that's about it. We've reached the end of confidence intervals. We've learned how they should be interpreted, how they should not be interpreted, and how they are calculated. I hope this video has answered your questions and cleared up any confusion. If you found this video helpful, please consider liking the video and subscribing to the channel. Thanks for watching, and I'll see you in the next one.